Hi, it's awesome to be here speaking to you in these strange times. Who am I? My name is Sara Bergman. I am a software engineer at Microsoft at the development center here in Oslo, Norway. I'm actually Swedish, but I realize that is a distinction which may only be important to Scandinavians, but I saw there were a few fellow Scandinavians in the chat, so shout out to you. In my day-to-day job, I work in a team under people services, and we own a set of APIs for profile data and profile images within Microsoft 365 and sort of beyond that as well. This is my fourth conference online. It's getting a bit less weird every time. Although the strangest things is not being able to see anyone, to just have like a screen. But I used to be a dancer, and when you're a dancer on stage, you have this really bright stage light in your eyes, so you don't necessarily see anyone then either. So I try to see the laptop as my stage light. All right, enough about me and back to what we're actually going to talk about today. Is machine learning sustainable? When we talk about sustainability and machine learning or AI, or really within the entire computer science field, we talk a lot about the computational need first. And the second part we sort of think about is maybe improving hardware. And as for hardware, it has truly been an enabler of both machine learning and AI, as AI has been an idea for like a long time, ever since Turing's article back in the 50s. But it's only recently that it's been infused in products and services that we see and use every day. So yes, if we can make hardware greener or only running hardware on greener energy, then machine learning can be a lot more sustainable. But is that enough? As we saw in Asim's talk, who was first, likely no. But that is the portion I'm attempting to dive deeper into on these next half an hour, 40 minutes or so. And I will take you with me on that ride. I will talk a bit about why this is important first. And then I will talk a bit about how we can measure carbon cost, how we can go from like a piece of code to like a value in CO2 that we can reason over. And then there will be a lot about research from the fields. I will cover papers and blog posts and some master theses, which try to point out the connection between energy consumption and accuracy for machine learning, as well as the connection between the amount of compute or work done and energy consumption. And then lastly, I will finish up with covering what you can do. If you're someone who writes machine learning code every day, but you don't necessarily know all that much about data centers, what can you do? Okay, let's jump right in. So why should we care if machine learning is sustainable? I think the first reason is obvious. The world confronts an urban carbon problem, and if we don't curb emissions and temperatures continue to climb, science tells us that the results will be catastrophic. Doesn't sound nice at all, so let's try and avoid that. As to how important the ICT sector is in comparison to other sectors, there isn't like a ton of new research. The most cited paper when you read other research papers is from 2010, and that one puts the ICT sector at around 2% of worldwide greenhouse gas emissions. And that is actually on par with the aviation sector, which when I first heard this, I found it quite ironic, because we talk a lot about flying and if that is green or not green, but we rarely discuss the impact of me watching Netflix on my couch or surfing on Instagram on my phone. There is more research from Europe from 2015, and they put the ICT sector as responsible for 4% of the European greenhouse gas emissions. We have to remember here that in Europe, we don't have as much manufacturing maybe as other parts of the world, which traditionally has a big chunk of those emissions. So yeah, the exact numbers are not clear. What is clear is that they're non-negligible, and we need to act, and we have the opportunity to act. The second part, which perhaps may be less obvious, is to democratize AI. If AI is really computationally heavy, it raises the barriers for who can do it. It basically limits this to companies, maybe universities, and one or two people who have the resources to do this type of groundbreaking research, which in the end limits everyone as research in the entire field is blocked. So how can you measure the carbon cost of your machine learning solution? You start typically by measuring the electricity. This is something that's been covered in David's talk, who was just before me, and also Asim, who was in the keynote. And this is done perhaps most easily by buying a watt meter, which you plug into a wall, and then you plug in your server or your laptop, and you start from there. You can also use different types of built-in tools to get a number on how much electricity you consume. There are some caveats to be aware of. It's not super simple, but it can definitely be done. But it's not always that you have, maybe you run in the cloud, for example. It's very hard to sort of knock on the door of a data center, like, can I just plug in my watt meter here? Likely that's not going to end well for you, so I don't endorse that. What you will then have to do is to estimate the electricity. And you can do this in rather scientific way, which we will talk a bit about later in the presentation as well. But it can be done based on things you can actually measure, and then based on that you can estimate. So now you have the electricity. How do you convert that to a carbon cost? You need the carbon intensity. This has also been covered a bit previously today, but basically the CO2 equivalent, which is sort of what we talk a lot about, and that is one value that we use, that we can convert all different greenhouse gases into like one single number. This makes it a lot easier to compare and reason over. For example, if I have 1 kilo of methane, that has the same global warming potential as like 84 kilos of CO2, but then it lasts a shorter time in the atmosphere compared to CO2, so that also takes effect. And already here, my high school chemistry is not enough to follow anymore. So this is very complex. That's why we need a simpler way that everyone who's not not an expert in chemistry can understand. And that's why we use CO2 equivalents. And how do we get to those CO2 equivalents? Yes, electricity always has a cost. Depending on where you are, the cost is going to be higher or lower. For example, I am in Norway right now, where we have like 98 or 99% hydro. Hydro is also very nice because it runs in the day and in the night, as long as it rains, and it rains a lot here, so we have a lot of hydro. We have many people before me have shared the electricity map, and Norway is usually below 30 grams, so it's pretty good. We're also exporting a lot. But if I were to sit in a different country, who, like Poland, for example, who burns a lot of coal, then the carbon intensity would be higher. So those are the two sort of main components when it comes to carbon cost. Okay, so what should we be comparing? As you know, depending on how you twist and turn your data, you can support different claims and paint different pictures. And I will use 2 different blog posts from the OpenAI blog to demonstrate what I mean. And those examples here will be on convolutional neural networks. What we could do is to compare the performance of different algorithms on the same data set with the same accuracy goal over time, and that will be the efficiency of AI. Or we could compare state-of-the-art to state-of-the-art algorithms from different points in time and look at how the computational need have changed over time. Sounds a bit complex? Let's break it down with a few examples. We start with the first one, which is efficiency over time. So here's a really cool graph. It's a lot of information, so let's try and break down the axes and then talk about what it actually shows. So it has years on the x-axis from 2012 to this year, and it has teraflop days on the y-axis. Flops is floating point operations, and you can think about it as a way to denote work that the CPU does. The whole graph is also in log scale. And what this graph shows, or what they did when they did this experiment, was to measure the amount of compute that was needed to train a a convolutional neural network on a data set called ImageNet, and then classified this to the same accuracy as AlexNet, which you can see as their starting point on the left. And basically what they did is to keep the performance of the system constant. And then they used open source re-implementations of publications of neural networks and measured the progress of this ImageNet data source over time. And this research only focuses on the final training cost of an already optimized model. So the development of this model is not included here. And what we see here with this graph is that since 2012, the amount of compute that is needed for this same task, essentially, has been decreasing by a factor 2 every 16 months. So compared to 2012, it now takes 44 times less compute to train a neural network to the level of AlexNet. And we talked about hardware in the beginning, so let's compare to classic hardware efficiency and Moore's law. If we have Moore's law during the same time period, we will get an 11-time cost improvement, which is significantly less. So that's very interesting. This proves that algorithmic progress in this area have yielded more gains than classic hardware efficiency, and it may continue to do so over time. It also paints like a really nice picture when we talk about carbon emissions and sustainability. We like it when graphs point downwards, and that's generally very nice. But we know that there is a strong focus within the machine learning community to obtain these state-of-the-art results. You can see this by there's a lot of like popular leaderboards, and they typically report accuracy as a measure or similar metrics, but they don't really have any mention of cost or efficiency of their solution. So while the last graph is really interesting, it is likely not the biggest driver of carbon emissions in the area. Okay, so what if we look at the second example? What happens if we compare state-of-the-art algorithms to each other and look at how the need for compute have changed over time? More graphs. Okay, let's do the same here and break down the axes so we understand what we're looking at. This graph also has years on the x-axis, but it's an older blog post, so it only goes until 2018. On the y-axis, we have petaflop days instead. And if you're thinking a lot about prefixes, I can tell you that a petaflop is around 1,000 times a teraflop. This graph is also in log scale. And what they did here is to show the amount of compute that was used in the largest AI training rounds. And the criteria for how they choose these models were threefold. So the selected results should be relatively well known, and they should use a lot of compute for their time, right? That's where the state of the art comes into play. And then, of course, give enough information so that they could actually estimate the compute needed. And then they measured the amount of compute, again, to train a single model. No development cost here either. And they chose this in both examples because they believe this number is most likely to correlate to how powerful our best models are. So what does this graph show us then? This shows that since 2012, the amount of compute used for these very large training runs have been increasing exponentially with a 3.4-month doubling time, which is quite fast. If we compare to classic hardware again and Moore's law, that would have that has a 2-year doubling period. That's a significant difference. So since 2012, this metric has grown more than 300,000x, and a 2-year doubling time would be like 7x. So this is quite a big difference. And it has largely been supported by more and better and more expensive hardware. For example, the use of GPUs and the increased parallelization we do. and better hardware will continue to have this accelerating effect on machine learning and AI. But on the other hand, the authors of this blog post argued that the cost will eventually limit how much we can do parallelization, and physics will eventually limit how efficient we can make our chips. So, in conclusion, this trend will likely not go on forever, but it is likely that it will continue in the same manner, at least in the short time frame. So this is super interesting, I think. The graph is less pretty though, and since we know that the carbon footprint is tightly coupled with the compute needed, this is an indication that machine learning may not be the greenest field we have in computer science. Okay, so by now, a lot of people are maybe thinking, what about all the good AI and machine learning can do for the environment? Can't we use it to decrease the impact of global warming, help us estimate the carbon intensity, or all these other things? Yes, completely, I'm with you there. I am not saying we should stop using all this great tech, because after all, the most carbon efficient software program was the one that was never written. But that's not what we're trying to do here. I'm also an engineer. I also like writing software. What I am saying, however, is that without this core stone knowledge of how to measure the sustainability of machine learning, we can't even start to reason over the rest. What we need to be asking ourselves are things like, how much carbon can I spend on developing my model before the cost of development is actually higher than the carbon savings? Or how long do I have to use these carbon saving AI solution until I've paid off that carbon depth of development? And what is actually sufficient accuracy for this task? And how much carbon am I willing to pay for that? What are our options to minimize this impact? These are the sort of things we need to be starting to think about and starting to reason over. But one great example of how we can use machine learning for good, I choose an example that was close to home. Expressen, it's a newspaper article in Sweden, and they still deliver newspapers to, I think it was 6,000 locations or something like that. Newspapers are very time critical, right? They're only really relevant on one day. So they started using machine learning to predict how many newspapers they should deliver to which place. And one of the effects that they measured or noticed was that they had fewer papers returned back to them. And that leads to less waste. I mean, it's awesome if we can recycle things, obviously, but it's even better if we can stop things being produced that are never going to be used. So I found that to be a very good example. Okay, we're gonna look at some more research now. This is a paper by Struble and a few other people, and it is heavily cited. What they did in this paper, which was one of the first, I believe, in this space at least, was that they characterized the dollar cost and carbon emissions of deep learning and natural language processing. So they did this in two parts. The first part was to calculate the dollar cost and the carbon emissions for training a variety of popular sort of off-the-shelf NLP models. And the second part of the paper was a case study to estimate the resources that were required to transfer an already existing model to a new task, or more the development cost. So how do we get to that? Well, they estimated the kilowatts of energy required to run this training, and then they converted these kilowatts into approximate carbon emissions and electricity costs. And that generates a bunch of numbers. And in order for us to understand what's behind those numbers, I think we're going to have to walk through the math together. So the first equation you see here is how we get carbon dioxide equivalents. So we take the power that was actually used for a task, and then we multiply that with something called the power usage effectiveness. This is a ratio which tells you how efficiently a data center uses energy. It's basically like how much energy is used for actual computing equipment compared to waste and cooling. And that's the first magic number here, 1.58, which is what they use in this paper. And that was the 2018 global average for data centers. And this basically means that 0.58 units of energy was wasted on non-compute tasks. And the goal is a power usage effectiveness of 1. And many data centers are actually heading in that direction. Okay, so that was the two first parts. The second part is the carbon intensity, which has already been touched upon quite a lot. I'm just going to mention the magic number they used here, which was 0.954 pounds. We've been using grams a lot in this conference so far, but now we're going into US research and then we're using pounds. And this was also the US average for 2018. So how did they measure power? They actually estimated it, but also measured it, but they didn't measure with like a watt meter. What they did is they measured the average power drawn from the CPU, the DRAM, and the GPU times the number of GPUs. And because those are going to be the main offenders, at least the CPU and the GPU are going to be the high spenders here. Okay, that was all of the math. Let's look to their actual results. So this was the first part, which was to calculate the dollar cost and the carbon emissions for those popular off-the-shelf NLP models. So there are two graphs here. The graph on the left is sort of just some average everyday examples for CO2 equivalents, because at least like that number doesn't say me anything. I need to compare it to something to understand what it means. So that's the graph on the left. The graph on the right on the other side is their results. So they have their 4 models, which is Transformer, Elmo, BERT, and GPT-2. And the column to the almost furthest right is the CO2 equivalents. And as we can see here, just training those models comes with a quite significant cost. For example, BERT is almost the same cost as a trans-American flight, which is quite a lot. NAS, on the other hand, which is the transformer, but they did the neural architecture search, that is 5 times a car lifetime. And that is a lot for just training. So this was the first part. The second part was to do a case study to estimate the resources required to transfer an existing model to a new task or develop new models. And this cost is going to be even higher than only training the models. So what they did here was to study the logs for the training of development a specific NLP model. The graph to the left is the same as before, just some everyday examples. And they only had the cost for this. They didn't actually publish the CO2, which was a bummer, but it's tightly correlated to the cost anyway. So it's still interesting to see. And what this paper shows here, like the graph to the right, is first the cost of training a single model, then a single tune, and then all of the models. It's a quite steep increase there. So in all, what should be our key takeaway from this paper is that the training an NLP model and developing new ones, it has a significant cost for the environment in terms of CO2. All right. So the next paper is not actually a paper, but a master thesis, where they aim to find a methodology for a fair evaluation of machine learning algorithms with respect to resource consumption. Because as we talked about in the beginning, many times research only publish their accuracy and that type of data, not necessarily the resource consumption. And this is also not a peer-reviewed paper, so the exact numbers aren't the most interesting, but the general trends is what we're interested in here. And what they did was they used 3 different image data sets and 3 different text data sets, and then compared 3 different machine learning modules. They used CNN and MLP, which are neural networks, and then SVM, which is a very simple machine learning algorithm. And what they did was to contrast the accuracy of these models with the training energy. So they actually measured the energy cost of the CPU and the GPU, which are the main offenders, and produced these results. So the number after the model here is going to be the number of epochs they run it for. And then we have training energy on the y-axis and accuracy on the x-axis. And what we see here is that for relatively little increase in accuracy, we pay a rather high cost in training energy. So it's quite expensive to move a few points up the right side of the graph, sort of. You also go very high. And we will see this in the next paper as well. So this is a paper called Green AI. And this is a peer-reviewed published paper. And they proposed making efficiency and evaluation criterion for research alongside with accuracy and related measures. So it's very similar to the one we just looked at. But this one is a bit more extensive. And what they also did was to divide AI into two different branches of AI. So they called one of them Green AI. And Green AI is research which yields novel results without increasing the computational cost, and ideally even reducing the computational cost. And then they also have Red AI, which is research that seek to obtain state-of-the-art results in accuracy or other related measures by using massive computational power. And Red AI is sort of what we normally think about when we think about AI research, but they argue that Green AI is also more democratic, as we mentioned in the start of this talk. They basically want anyone with a laptop to be able to do Green AI research. So what they did here is they didn't measure, but they suggested a completely new metric, or not completely new, but they suggested a metric, which is floating point operations, FLOPs or FPO, as this concrete measure. And FPOs is the total number of floating operations that was required to generate a result. And FPO is really good because it provides an estimate for the amount of work that you need to perform for a computational process. And it also is very correlated to the time you need to run it. So therefore, it's also good. If this is the first time you hear about the floating point operation, no need to be confused. You can think of it as a way to characterize what your CPU is doing. Like you can define a cost in floating points for like basic CPU operations, and then from these basic CPU operations, you can like derive the cost of like more complex tasks your CPU does. And it's good because that's going to transfer between platform, that's going to transfer between softwares. It's really a good way to compare different things because it's like this small common divider. Or yeah. All right, so let's look at some dashboards. They used existing metrics to showcase how this metric could look like. So we have two sets of graph. The graph set to the left is very similar to one of the first blog posts we looked at, which is basically different models from different years. And then the one to the right is one model, but all the different layers. And the top graph is the accuracy, the two red ones. And then in the middle, they have this new metric, floating point operations in billions. And then the bottom graph is the number of parameters in millions. And I found this really interesting because what I found most interesting is how accuracy ties into computational cost. If we look at the graph to the right, we see that we increase like 1 percentage point from 77.4 to 78.4 in accuracy. And for that, we almost double the number of floating point operations. And it's like a big difference in the amount of compute we need to do, and therefore the amount of electricity, and therefore the amount of carbon we emit, just to get that little bonus in accuracy. It's very similar to the left graph. After we come above 78% accuracy, like you don't have a huge impact in accuracy, but the floating point operation is like continuously going up. So that was very interesting, I think, the first time I saw it. And that was all of the research. Good work for making it through. I know it can sometimes be very dusty, but now we're done with the research, and let's summarize and look at what you can do instead. So what we've learned from all these papers is that machine learning comes with a significant compute cost. And we know that this compute cost translates into a significant carbon cost. And there are also indications that this is getting worse over time rather than better with time. But there is light on the horizon. We have seen that the efficiency of machine learning is getting better. We are literally getting more bang for less bucks if we can settle for less than state-of-the-art accuracy. There are also more and more research in this field, and this question is being asked and answered a lot more now compared to just a few years ago. So what can you do? Reduce, reuse, recycle is something that we talk a lot about in waste management. I hope you heard it. And it can actually be used here as well. My dad used to work in waste management, so I know there are more things you can do besides recycling, but I didn't have a good analogy for how you could burn your code to heat houses. So I'm going to stick to these three. Okay. The first thing you can do is reduce. So you can reduce your accuracy hunger. What do you actually need for this task? What's the accuracy that is sufficient for what you're trying to achieve? And how much carbon are you willing to pay for that? Here you also have to think about the risk, obviously. Some things you can't safely decrease the accuracy because there is risk to maybe humans or machines or something that you're not willing to sacrifice. That's okay. But for other things, maybe you can safely decrease the accuracy for like a recommendation service of some sort. Yeah, you might see increased sales if you recommend that little bit better, but this also correlates like an electricity bill. If you have to double the amount of work you do for that little increase in sales, like will it even break even in terms of cost? Like those are the things we need to start to think about. You can also reduce your carbon intensity. That's sort of the second part. The first part is like, how can I do less, use less electricity? And the second is, how can I make sure that the electricity I use make the least amount of impact? And that you can do by reducing the carbon intensity. You can plan the training of your models, like when and where you run them. For example, we know that there are some times when the grid is going to be really choked. Like when everyone is starting the washing machine in the morning and using the shower and all those things, maybe that's not the good point. Maybe it's another point in time. You can also reuse other people's models. You think about other open source models available, and that way can you like cut out the development cost and only, in parentheses, pay for the training cost of your model. And then pay that forward as well. Are you able to publish your work as open source to sort of let your development cost be worth something for others as well? And thirdly, you can recycle your own machine learning and AI solutions for new problems. Maybe they don't fit for type A problem anymore, but maybe they're super great for type B, and therefore, again, not pay that development cost. All right. Thank you so much for listening. Now I believe I have time for some questions.